Now we are streaming. Sorry? Yep.
No, I just said good call.
Yep, very good. Yep, good to check. So what we'll do today is to pick up from what we left off last time. So let's go ahead and figure out what was the last thing that we talked about last time. This is the actual reason why I do all this screen recording. So that I can remember what I talked about in the previous lesson.
Last time, I think it was something about your wet food for your cat and
well, there was that, and there was something else too, right? So 4 days ago. Okay, so we have calling and returning already.
Oh, and then twice yesterday. Passing by value. Yeah, that was recursion, wasn't it? With subfunctions and assembly?
Yeah, we have a recursion, but it doesn't pass pass parameters.
Yeah.
Okay. All right, so that's where we stopped. Very good. Okay. So getting back to the modules, this is what we have. So today we'll talk about how to return a scalar value. In other words, if I give you a function, it's a very short slide here. So we'll take a look at this one. It's really, really short. Okay, open new tab. There we go. Okay, so the question is, if you have a function definition like that, how do you do it in assembly? Or normally, how do we do it in assembly? You're returning a scalar, so scalars basically refer to anything that is quote-unquote small enough to fit in a register. That's the idea. So in this case, an integer typically would be representable using a register, regardless of the architecture. So when you want to return an integer value, it is just being stored in a particular register. So in the toy processor that we are dealing with, I just choose to use register A as the register to specify the return value. Then you guys might think, okay, but that's good for the toy processor. What about the Intel processor then? Well, the Intel processor would use EAX as a register. Okay, it would just, for each architecture, it would just specify a particular register as the one to return a scalar value. Is that okay? So now you will say, well, how do we know that is actually true? I mean, how do we know that is the standard of all programming languages? All C programs will boil down to using a particular register to return a value. So this is something that you can do on your own too, and it doesn't limit to what kind of architecture you're dealing with. So what we'll do is we'll write that really simple program. We'll just call it 5. And we'll say 5 as a subroutine returns the value of 5. Okay, now if you want to use some more obscure value just to be sure that we don't accidentally end up with a value of 5 in a particular register, just pick whatever you want. Okay, because there's always a chance 5 is not a very uncommon number to be used. So in this case, I'm just going to call 5 here, okay, which is okay in C. In many other languages, if a function returns a particular value and you're not using it, it's a big no-no. Okay, but C let you do this. Okay, which is not always a good thing. So we'll save this program. GCC-G -O5.c, compile the program, and use GDB to run the program. We'll put a breakpoint at line 9, which is the return. And we also put a breakpoint at the beginning of the main subroutine, just so that we have an idea of what the values of the registers are. So we run the program, and IR basically lists all the registers. So you can see a whole bunch of registers, but none of these is actually 5. More specifically, these are the registers that are typically used in calculations with the x86 architecture. These ones are extended because we are using the 64-bit instruction set. The 32-bit instruction set only has the first 8 registers, but the 64-bit instruction set has these additional registers. And you can see these registers have no particular names. They're just enumerated as R8 all the way up to R15, as opposed to the first 8, which actually has names. The other thing that most people do not know is A, B, C, D, they're not really just sequential. In other words, Intel did not choose A, B, C, D because they are sequential letters. A actually has a meaning. A stands for accumulator, B is base, C is counter, and D is destination. So each one actually has a very specific meaning, because at one point in time, the ancestor of the Intel architecture is a special purpose register architecture, which means certain instructions use specific but implicit registers, as opposed to, oh, every instruction can use any register in the entire bank. The TTP, on the other hand, has general purpose registers. If you can use A for addition, so can you can also use B, C, D as registers for addition, subtraction, compare, and so on. So I do not build in any special purpose instructions, or any instructions that imply the use of special registers. Yep.
So the 64-bit instruction set has, looks like 16 registers, well, 17 if you include the RIT one. Would a theoretical 128-bit instruction set have 32 registers then?
Absolutely. It all depends on how they want to allocate the bits within an opcode to specify which register they want to use. But this is also the reason why it's not backward compatible. The 64-bit instruction set is not going to go backward compatible to the 32-bit, because the format, the way you allocate the bits and what each bit represents is now different. So that's why it has to break the code, the binary compatibility, in order to do this. All right, but we can observe that none of these is actually 5. Okay, that's the whole point. So now we continue execution, which means we are running the program as fast as we can until the next breakpoint, which is right at the return point. So now we do another IR, or info register, and we can see RAX has a value of 5. In the case of the Intel architecture, the 64-bit Intel architecture, or the AMD 64 instruction set, GCC uses RAX as the register to contain the return value. Is that okay? All right. Now, why do we want to know this? Why is this of any importance to us, other than curiosity? This allows you to write code in a way that you can write a subroutine in assembly, but it's callable from C, because your assembly code knows how to communicate with your C subroutine. And the other way around. You can also call a C subroutine and understand that when the C subroutine returns to your assembly code, register RAX in this case contains the result or the return value of the call. Okay? Which is kind of interesting because it allows you to write code that is partially in C and partially in assembly language, which can be handy. Why would that be handy? Why do you want to learn how to program in assembly when C compilers these days can do optimization better than most programmers can manually do it?
Debugging.
Debugging would be one, okay? So that's one, good for debugging purposes. But understanding the architecture and how return values are done in this case would also be useful when you're trying to reverse engineer a program. In other words, when you try to decompile a program to figure out how it gets certain things done, this can be very useful. What else? There's certain kind of code that can only be done in assembly, but not in C or C++. What kind of code are we talking about? In what situation you can say, okay, I cannot do this in C or C++?
Operating system.
Only a portion, okay? A portion of the operating system, particularly very deep within the kernel, the part that deals with processes, handling processes, and also handling threads, cannot be done in C or C++ because it becomes a chicken and egg problem. So C does not have the vocabulary to specify what needs to be done when you want to switch from one thread to another thread when you have a multi-threading type of process. So that has to be done in assembly. But you don't want to do it in assembly in a way that you can no longer use C to interface with that code. because you want to have a multi-threading program where your C code can explicitly say, okay, I'm going to stop here and let that other thread go. Or I want to communicate with that other thread. I want to unlock a thread that might be pausing because of waiting for a certain resource. So you wanted to have a C interface to your multi-threading library, okay? And this is what allows you to do it, okay? Because now we understand how C code is done, the interface between the caller and the callee. So when you write code in assembly, as long as you follow the same rules, there's no problem of your assembly code calling C, and also there's no problem with C code calling your assembly code. Is that okay?
Will you show us that? Will you show us an actual not like right now, but eventually?
Not with a toy processor, because because I don't have a C compiler for the TTP. Yeah. But I can show you this example. arccis.net is under my stuff. So it's under develops. It's my real-time kernel. So at one point in time, I wrote a small, tiny little real-time kernel for the Avr architecture. The Avr architecture, for most people, it's like, okay, what is the Avr? The Avr architecture is the one used in all the Arduino boards. So all the Arduino boards make use of a particular variant of the Avr processors. They're really kind of cool because they range, in terms of pricing, they range from like 10 cents each all the way to maybe $8 or $10 each, depending on the resources available. So my entire real-time kernel is written in assembly. There's not a single line of C code. However, there's an API. So the API is written in C entirely. So I have structs, I have subroutine calls. This is how you initialize a particular, the real-time kernel itself. So that's why it is useful, because I wrote the entire real-time kernel in assembly in order to make it efficient. And also there are things that I cannot possibly specify in C code. Like, okay, let's put all the registers over here in this part of RAM and then restore the registers from another chunk of RAM. I can't do that in C code. There's just no way to specify those operations in C code. But at the same time, I need to be callable, okay? My code needs to be callable from C in order for it to be useful. Okay. So there's a whole bunch of API. I can add a thread to the multi-threading system. I can a thread can commit suicide, which means that the thread terminates. A thread can be killed by another thread. You can schedule a thread in the future. In other words, you can say, okay, this particular thread, wait for X many ticks. And each tick is basically a time interval. It can be a millisecond, can be a quarter of a millisecond, depending on how I set up the timer. So it's really kind of handy. You can also use semaphores, which is way beyond the scope of this class. But semaphores basically allows threads to coordinate. Like if you have a section of code where only one thread should get in at any particular time, you can use semaphores to lock out other threads. So if multiple threads want to use the same section of code, but only one really should be using it at any particular time, it is a way to synchronize your threads and go like, nope, somebody is using it, you have to wait. But when that someone is done using that section of code, then it will automatically do another operation. So if anyone else is waiting to get into that section of code, which is called a critical section, the multi-threading kernel will do whatever it needs to do to say that, okay, it's free now, and since you have been waiting to use this section of code, you can use it now. Okay? But all of these are called C callable. But the program itself, the real-time kernel itself, was written entirely in assembly code. Can anyone guess the size of the real-time kernel? It can do multi-threading, it can do round-robin thing, which means, and also preemptive scheduling. If one particular thread decides that I'm going to hog all the resources, I'm not giving up, the real-time kernel will kick in and go like, nope, it's time for another thread to get some execution time. So can anyone guess the size, the footprint of this kernel.
50 megabytes?
It's 2 kilobytes.
Okay.
I'm guessing 1.
2 kilo, 2,000-ish bytes. That's the size of this tiny little kernel. But it doesn't have a file system. It doesn't do TCP/IP, has no networking capabilities whatsoever.
No graphical user, just
No
planning.
GUIs, nothing, right? But it does do the multi-threading. It has what we call priority queues, which means your threads can run in different priorities. And if a higher priority thread is active, the low priority threads have to give up and say, okay, you get to run first. It is basically designed for embedded system or robotics, where certain things definitely has to take precedence.
Okay.
Yep. So,
Yeah, that was no time.
but it's an illustration of why you might want to write assembly code that needs to be called from C, and sometimes it's the vice versa as well. All right, so that's that. So getting back to returning a scalar. So are there any questions about returning a number, or the rationale of why do we care, how a value is returned, or how we call a subroutine, or how to return from a subroutine? Questions? Yep, go ahead.
Okay, so so you're loading into register A specifically because you want it to be able to go between C and
Assembly code. Right.
Otherwise, you could use whatever register you so chose.
That is true. However, okay, let's say you're writing subroutines only completely in assembly, and nobody's going to call your subroutine, and you're not going to call any C subroutine. But if each time you have something to return, you choose a different register, it won't be very long until when you say, okay, but I cannot remember for this particular subroutine which one is the register that is returning the value. So it is still good to have a standard, so that every single time you say, okay, I know this is returning a value and it has to be in register A, because that's the standard. Yep. So everybody's doing okay so far? Right, cool. So the next module, that's the end of this module. The next module is actually a little bit more complicated, because this one talks about how to pass parameters to subroutines, and the way it's done here is also C compatible. In other words, I'm using TTP because that's the architecture that we're using in this class, but the approach of doing this is also the same in GCC for your AMD 64 instruction set. Okay, so it's the same idea. It's just that I'm using a very small, tiny processor to illustrate the idea. So the first idea, or the most important part is the parameters are on the stack. Okay, so when you are calling subtraction 3, 5, okay, and I think we have the C code somewhere. Okay, so let's say this is the actual subroutine itself. This is the subroutine in C that you want to implement in assembly. We know how to do the return x minus y already, because we just mentioned that the return value is through register A. So we got that part done already. The most important part is how do we pass arguments to these parameters? This is the callee or the subroutine's perspective. The caller looks like this in C. So the question now is, how do I specify that 5 is the second argument, 3 is the first argument, and in the subroutine, I know where to find x as a parameter and where to find y as a parameter. In other words, this is once again an agreement between the caller and the callee. The subroutine being called has to agree with the calling code so that one can specify the parameters or the arguments, and the other one knows where to find those parameters. Is that okay so far? And many people will think, oh, we can use registers for this purpose. Well, the answer is yes, we can, but there are only so many registers. In this case, we only got 4 registers. And how many parameters can you specify in C and C++ for any particular subroutine? You can have as many as you want, exactly. So the point is, we may not have enough registers to pass parameters. Correct. Yep. If it is in RAM or in the, because stack is in RAM, so that means when we use the approach of passing parameters on the stack, that means you have to know where to find it. But we don't want to use static locations, okay? Because if you use static locations, you're wasting a lot of memory. Okay, let's think about that approach. So if you think about using static locations, like each subroutine definition will designate a particular chunk of memory to be its own, parameter space. Okay, that's really wasteful because the question is how many functions are actually in use at any particular time of the execution of a program. Not necessarily, because one function can call another function. So, but you're close because it depends on how deep your call stack is, right? So function main can call function A can call function B can call C can call D. So the question is, how deep can it go? 20 levels? 30 levels? 50 levels? 50 levels is a lot if you think about it.
Recursion is also level of depth, right?
Yes. So when you're dealing with recursion, yes, we can definitely go really deep, but short of recursive subroutines, 50 levels is really deep. Okay, if your program that is not recursive is reaching like 50 levels of call from main, that's considered pretty deep already.
It's complex as hell too.
Exactly. But how many functions do you actually have that is already compiled into your program? Is that going to be 50? Can be easily 500, right? You can easily have 500 subroutines, but at any particular time, only up to 50 is actually active. So if you allocate static space for passing parameters, you are wasting a lot because a lot of that space is not even used.
So these are like static ints for certain functions.
Right. So using that method sorry?
So you're saying try to avoid those, or just saying?
Exactly. I'm trying to avoid that. Because the other downside of using a static location for parameters is you cannot do recursion anymore. Because recursion relies on the ability to store different parameters as well as local variables per invocation. But if you allocate a chunk of static location for the parameters, you only have space for one invocation. You cannot do recursion anymore. Does that make any sense?
Kind of. So if I have a static int and my base case has to go to 0, and I decrement the static int, are you saying that recursion is not possible anymore?
Recursion, it needs two things, right? It needs to have per invocation allocation of resources. So if you only have static location, then all the invocations will be sharing that location, which is going to be problematic.
Okay, so then it'll be infinite because it'll go to 1.
Yep. Okay, and then some people will say, but who's going to use recursion, right? I mean, other than Professor Fox, who says recursion is the best friend, right? Data structure, but everything that is recursive can be done without recursion. So one can make that argument and say that we don't really need recursion. We can do without recursion at all. Fine. So let's say I buy that argument. Even with that argument, it still doesn't make sense from the perspective of C and C++, which supports multi-threading, to have a static location for parameters. Okay, so this one is a little bit more complex. If you don't get it, don't understand this part, it's okay, it's not a problem. But I do want to illustrate it because when you do get to one class where this is brought up, then you go like, oh, okay, I understand that. Okay, so I'm going to illustrate multi-threading here, okay? And multi-threading is easy, okay? It's basically just having functions of the same program, and those functions are executing at exactly the same time, okay? Okay, because we do have multi-core now, so they can actually be executing at exactly the same time. So we have thread 1, this is T1, which is a thread going like this. This is a thread T2, which is going like this, okay? And they're going in parallel. Is that okay? So thread 1 decides, I'm going to call string and copy. So this is calling string and copy, okay? All right, so string and copy is going on just like this. And then at some point in time, the operating system decides the multi-threading part of your OS is going to kick in and go like, hey, thread T1, you got enough execution time already. Let thread T2 have some execution time too. So T2 is now going to call, guess what? The same function, string and copy. And if your parameters are stored, okay, it's kind of fuzzy. Let me refocus. There we go. So if you are using a static chunk of location to store the parameters as well as local variables for string and copy, you're in big trouble because the first call to string and copy from thread T1 is not done yet. But then the multi-threading kernel decides, hey, we'll give T2 some time to execute, and it decides to call string and copy. So now you have a problem because when T2 calls string and copy, it's going to overwrite the parameters that are already stored in static locations coming from T1. Okay, so either way, okay, you have a problem. If you interleave the execution of string and copy, it'll be really bad. If you let T2 finish first and then resume T1, it's still bad. Okay, because in either case, there's corruption. So the only solution to solve this problem, okay, if you want to maintain the use of static location for passing parameters and storing local variables, the only way to solve this problem is to lock out T2 from calling string and copy until T1 is done with it. But that is very unreasonable, okay, because T2 now has to wait for T1 to finish. What if T1 takes a long time to finish? Then T2 cannot continue. Does that make any sense? So that's not reasonable. So this is why we don't want to store parameters or local variables using static area. We want to use dynamic area for that purpose. Dynamic, what do we mean by dynamic? What do you think? We're going to use. Sorry? Oh, we can. Well, with this scheme, we can run multiple threads at exactly the same time, because we're going to use the stack.
It's created as needed.
Sorry?
That's created as needed. For dynamic?
Yeah.
If it's created as needed?
Yep, it is created as needed. Very good. Okay, so it's basically just-in-time allocation. If you don't need it, we're not going to allocate it. But when you need it, we'll allocate it on the fly. And each invocation now has its own parameters as well as local variables. All right, so what we'll do is we're going to look at the call, and then later on we'll talk about how it's done. So we'll say, we'll call the subtract subroutine. So call subtract 5.3, okay? So what we want to do is to say, hey, we're going to push all of these on the stack. So the way we do it is, okay, remember when we draw the stack grows in this direction. As we put more items on the stack pointer gets lower and lower and lower. Okay. So what we'll do in this case is we're going to put 3 here. We'll push the value of 3 first. So 3 ends up with a higher value than the 5. Then we push 5. And then we also do the same thing as what we talked about last week, which is calling. So what do you do when you call a subroutine? Not worrying about the parameter stuff. When you're just calling and returning from a subroutine, how do we make use of the stack in calling a subroutine?
First out.
Push the return address. Okay, we have to push the return address. So the return address is going to be pushed at this point. This is the return address where we are supposed to go back to. So after these 3 items are on the stack, then we can pass control or jump to the subroutine itself. So from the subroutine's perspective, okay, which I'm going to use green here. From the subroutine's perspective, the stack pointer is pointing to the return address, but it can also expect parameter 1 to be right next to the return address and parameter 2 right behind it. Let me say that one more time. From the perspective of subtract as a subroutine, it can expect the stack pointer to be pointing to exactly the return address because that's the protocol between the caller and the callee or the subroutine. But using this particular standard, it can also use the stack pointer to locate the first parameter. In this case, it's the 5, and also the second parameter, which is the 3. Is that okay? So now, when we look at the subroutine itself and subtract int x int y, when we need to access x and y in this subtraction, it knows that x is here and y is over here. 1 byte beyond the stack pointer is x, 2 bytes beyond the stack pointer is y. So is that okay from the perspective of just looking at the C code, the caller versus the callee, or the subroutine being called? Is that okay? All right. So now the question is, okay, if this is what we are doing in C and in terms of the picture, this is what's happening on the stack, how do we do this? Okay, that becomes the next question. So for the subroutine, for the call itself, then they use red here. So for the caller, the first thing it needs to do is to push the 3, and then the second thing it needs to do is to push the 5. So to push those two, it's LDI, use whatever register you want, 3, and then we do a decrement of the stack pointer, and then we do a ST for store, indirect to what D points to, and then register A. That will put this put the 3 on the stack. And then we do something about the same, which is LDIA with 5 this time, decrement the stack pointer again, and do another ST instruction. These 3 instructions will push the 5 on the stack. And then the rest is something that we talked about last week already, which is pushing the return address on the stack. And then we do an unconditional branch to the subroutine called subtract. Is that okay? Or not?
Can you just say that one more time?
Okay. So the rest of the code, okay, I can just continue over here. So the rest of the code is to push the return address. So it becomes LDIA and then whatever label you want to use for the return address. And then decrement D again because we're pushing something on the stack. And then another ST instruction to store the return address on the stack. And then we can now do a JMPI instruction to jump to the subroutine called subtract here. In other words, these 4 instructions, okay, these 3 to be more specific, is responsible for the return address being on the stack, but together, this is actually just calling subtract as a subroutine. Oops, oh, okay. I guess I have to hand this one over a little bit. There we go. Okay. Is that part okay? So the red code is corresponding to the caller, okay? The one who's calling the subroutine has to do it this way. Now, when the subroutine returns, the return address will no longer be on the stack because the subroutine itself is consuming the return address in order to get back to this place here. Okay, so return address is basically just a label to identify where we're going back to. But when we get back here, the return address is no longer here, so the stack pointer will be pointing to the 5. Do we still need that 5 on the stack? It's a parameter, and the subroutine is already done, so we don't need that, right? So we need to increment, because in order to allocate, we do a decrement, so that means in order to deallocate, we do an increment. So this increment D is going to deallocate this part here. So it's going to deallocate the 5, and then another increment will then deallocate the Y. So after these 2 are deallocated, then the stack pointer will now be pointing back to this position, which was where it started off with before the call to subtract. Is that okay? So the red code is basically illustrating from the caller's perspective of how to push parameters on the stack, how to push the return address on the stack, continue execution in the subroutine, When the subroutine is all done, we go back to the continuation point, which is called return address in this case, and then we have two increment Ds in order to deallocate the parameters that are no longer needed on the stack. Yep.
Okay, so the position that the pointer is at this time at the end of this,
Mhm.
if we wanted to put something into the position where 3 was, we would need to decrement the pointer.
You mean the stack pointer?
Yes, before loading something there at the position it's currently in.
So technically speaking, once you deallocate a byte on the stack, you can no longer guarantee that it will still be there. Which is kind of weird, right? So who else is going to come in here and mess around with the stack? So we haven't really talked about it yet. It's called the interrupt. So an interrupt can kick in and use whatever is below what your stack pointer is pointing to without asking you first. So once you move the stack pointer up beyond a certain point, whatever is below your stack pointer is subjected to change already because of some background stuff that can happen. Okay? So are we still doing okay so far with this code? More or less? Okay. All right, so now the next question is from the callee or the subroutine's perspective, how do we, when we get to subtract as a label, how do we get back to parameter x, how do we get back to parameter y, and then perform the subtraction? And then store the result in register A, because that's what we talked about earlier today in class, is the return value is stored in register A. Is that okay? So let's figure out how to do that part. And I might be running out of space on this piece of paper, but I'll give it a try. Okay, so let's say this is subtract. Okay, subtract. Okay, and we do move it just a little bit like that. There we go. So this is subtract. What should we do first? I think we need to get to x and y, right? Okay. And ideally speaking, I want to put x in register A so that when the subtraction is done, the result is already in register A and I don't have to do a whole lot of extra work. Okay. So now we need to figure out the address of x on the stack. Where is it? It's 1 above where the stack pointer is pointing to, right? But I better not mess around with register D. Remember, if you increment D, it means whatever is below that can be is subject to change. So what we want to do is to make a copy first. So we use a CPR to copy register. You can use a variety. So I'm going to use A here so I can reduce the number of registers that I need to use. So I'm going to copy register D to register A. So now register A is pointing to the same location. Is that okay? And then next, I'm going to do an increment. So register A was pointing to the return address. Now it is pointing to the 5. Is that okay? And then we do a load. LD A with A. So I'm using A to both specify the location of what I'm retrieving from RAM and also store the actual content at that location. Then I lose A.
Then you lose the address.
Then I lose the address, so I have to do another CPR. So from here we go to another CPR. This time we use register B, D, increment D, increment B, don't mess around with D. And then we do another LD. Oh, we need 2 increment now. Okay. Yep, increment B, or I can do another CPR down here. But that's okay. This is just making it a little bit longer. LD, B, B. Okay, so let's take a look at these 4 instructions. So for the first instruction, B would point to the return address because I never moved D, right? If D was pointing to the return address, it is still pointing to the return address. The second instruction would move B to point to the 5, but that's not what I want. I want parameter Y, not parameter X. So I increment it one more time. So now it is pointing to the 3. Then I do the dereference here and say, hey, register B, I want to get the content in RAM where you're pointing to. So now your register B has the value of 3, which is Y. Yep.
Stretching.
Oh, okay. Yep.
So this comes after the increment B, increment D, right?
Increment B, increment B. Yes. So increment
Sorry,
B,
the other side.
B.
The D.
My D.
Yeah. So after the address, return address, you have increment B.
But wait, this is from the caller's perspective. This is what we do to clean up.
Okay. Oh.
From the caller's perspective. This is what the subroutine itself is doing. So the blue part is the assembly code for the subroutine. The red part is from the caller's perspective. Okay. All right. So what do we do? What do we need to do now? Register A has X. Register B has Y. We just need to do a subtraction, right? Okay. So we do a subtraction. We are subtracting B from A. So the A ends up with X minus Y, so we're all done because that specifies the return value. Then the next thing we need to do is to do an LD. This time we can reuse register B. So we are saying, okay, B, I want you to store whatever the stack pointer is pointing to. Remember, the stack pointer is still pointing to the return address, okay? So at this point, B becomes the return address, or it points to where I'm supposed to continue execution. But before the jump, I got one little thing to take care of. I got to deallocate the byte that is now storing the return address. So to deallocate that, I just need to increment D. Then we can do a jump instruction to go back to whatever B is pointing to. Then we get back to this point, and the rest is just cleaning up after the call itself.
So the load is, I'm going to jump here, I'm going to get rid of this variable, quote unquote variable, and then I'm going to do the jump. Load is, this is where I'm going to jump to.
Right.
Increment is getting rid of that variable of the stack.
Yep.
Then you're jumping.
Yep, exactly. So the load instruction is going to copy return address to register B. The increment D instruction is going to make register D to point to the 5. And then the jump instruction will continue execution with the increment D instruction right at the label of return address. Okay. So are there any questions about the code here, or why the code looks the way it is? Yep.
Sorry, can you repeat why we're loading the content of D to B register?
Why we are loading the content of
And then
D to B
pretty much the last 3 pieces of code.
in blue?
Yeah.
This is the return. Okay, so this part is just calculating X minus Y,
Right.
and then use it as my return value.
Okay.
Okay? This part is just the usual return sequence code. Whenever you return from a subroutine, you are expecting the stack pointer to point to the return address. So that's why we use the LD instruction to say, okay, whatever the stack pointer is pointing to, store that value, which is the return address, to register B. I cannot use register A anymore because register A is now specifying the return value. I don't want to overwrite it.
Where is D at that exact point before you increment?
Right at this point?
Uh-huh.
So right at this point, register D will still be pointing at the return address.
Okay.
In other words, from the entry point of the subroutine all the way up to here, register D is still pointing to the return address. The next instruction is going to move the stack pointer up, so that we are no longer pointing to the return address, which makes sense because I just used it. I put it into another register.
But
Right?
But didn't we clean that up afterward?
Huh?
Didn't we move, like, after we come out of the subroutine, didn't we?
We move, but those two are corresponding to the parameters, not the return address. There are 3 things on the stack right now. Well, 2 remaining, but there were 3 things on the stack. One is the return address. It is the responsibility of the called subroutine to clean up after the return address. But it is the caller's perspective, caller's responsibility to clean up the parameters. Is that okay? Yep.
Would you have to clean up B then, since your B is still pointing to a return address?
No, B is basically all the registers are what we call scratch registers. In other words, whenever you call a subroutine, you have to assume register A, B, and C cannot maintain the values. Yep. Which also means if you need to save anything, you have to put it on the stack first. Then you call the subroutine and then you restore the value of the registers. Yep.
Do you subtract subroutine? Is it JMP or JMPI?
This is JMPB because it's not immediate. The other one is JMPI because it is immediate.
What do you mean?
Immediate means you're specifying exactly where it needs to go. You're specifying the constant. Subtract is a label corresponding to the entry point of the subroutine.
And JMPB has to go into and get the content and then.
No, it is just copying register B to the program counter. That's all it does. It's just literally taking the content of register B itself.
It has to do something before it can jump.
Huh?
It has to do something before it can jump.
That's exactly how it jumps.
Yeah. Instead of JMPI, it's saying, okay, where am I jumping to? It's that way.
Right.
Okay.
Yep. And you cannot change this part easily because it's not a register.
Yeah.
It's like using like comparing to C's like constant int and int, where those are like you can't change constant ints, but you can change ints. If you know what I'm trying to say.
Sort of. Well, if you look at the microcode of JMPI versus the microcode of JMP, that will illustrate, how each opcode works. And that's why I give you the entire architecture and all the microcode slices, because eventually it is the microcode slices in the ROM that determines what is done when you have a JMP-B instruction as opposed to a JMP-I instruction. So that's something you want to experiment with, when you're trying to study for this class, is just to experiment with JMP-B after initializing B with something, as opposed to JMP-I, and then you look at what happens, what pathways are established inside the processor architecture. Is that okay? All right. Well, this is a lot of talking, so it's time to do some, actual coding, right? It would be a shame if we can just talk the talk but not do the walk, right? How is that phrase? Walk the walk, right? You can do the talk. You can talk the talk, but can you walk the walk? Yeah. So let's go ahead and do it. Okay. So I'm going to use just a plain text editor here to type in the code. So this is starting from the beginning. So the first thing is we have to initialize the stack pointer, and we initialize it to 0 because the moment you decrement 0, it becomes FF, which is the highest location in the toy processor. So this is officially the entry point of main. It is useless other than just for documentation purposes. So inside main, we are going to call subtract, but before we call subtract, we have to pass the parameters. So this time we'll use, well, I'll just be consistent with the document camera. Okay. So the next one is decrement D and then STBA, and then we have the 5. Decrement again, store.
You left out the D.
Oh. Well, let's see what happens when I give this to the assembler.
Okay.
The assembler should check for most errors. Okay, maybe not all, but most errors it should catch. So now we move on to pushing the return address. Okay, I'll just make this really long. Okay, push return address. And this is also a good time to kind of mention, do not confuse the return address with the return value. The return value is the value of the expression next to the return keyword itself. The return address is usually hidden. You cannot see that in a C program. Okay. So we do another decrement D, store to DA, and now we can do the JMPI instruction to subtract, which is the name of the subroutine. And this is where we define return address to main, where we only need to increment D twice to clean up after the parameters. So D allocate stack space for parameters, and that will be the end of the entire sequence. Okay, I'm not storing the difference anywhere. It should still be in register A after this is all done. And now we specify the subtract subroutine. And the first thing we do is to copy A to D, D to A, okay, A equals D, and then we increment A. So now A is the address of parameter X. And I'm gonna do another CPR here. So I'm changing the sequence of instruction a little bit just to make it slightly more optimized. So I'm copying A to B, okay, B equals the address of X2. And then we do the LDAA, so that A used to be the address of X. Now that we dereference it, it is just the value of X, the parameter. And then we can do about the same thing with B, but I saved myself a little bit of code here because now B is the address of Y, because I made a copy earlier when it is still making sense. And then we can do another LDB with B. So the B is the dereferencing of B, which is also just the value of Y because it used to be the address of Y. Then we can do the subtraction. Just like that. And now we can do the return sequence, which is LDB with D. B is the return address, okay. And then we increment D, allocate return address from stack, and then we do a JMPB, continue, and caller. Okay. So I'm claiming this code should work, right? Except for the one that we know it's not gonna work. Okay, so we go back to here, we go to the folder. Come on, scroll down. Yep, I'm just trying to find. Interesting. It doesn't have a scroll bar all the way to that side. Here we go. Shared. And then we have the assembler. There we go. Paste. Should get an error message. It's doing a recalculation, and right here it complains about register X is expected, register Y is. It complains about both because this is both register X and register Y, so that's why it is complaining both of those. It's misleading. Go to the RAM file, download. Okay, save. We'll call this subtract. Now we can start up the simulator. All right. So I think I got the ROM updated here already. So the trick that I was trying to tell people to do is to disconnect this reset line. So this way, when you reset the whole thing, when you reset the processor, it doesn't reset the RAM as well. There's one more little trick to do this whole thing. The clock needs to be reset to off either also when you reset. And I don't think this is automatic. If you have a control T and this is high, when you click reset, it doesn't reset the clock to low, unfortunately. So that's kind of an issue because if the clock starts high to begin with, then everything will be off phase by one click, which is a problem.
Sure.
So yeah, so you have to kind of make sure the clock starts with a low state also. If you use Control R, that will be done too. So if you have a clock that is already high, and you do a Control R, which is reset the simulation, Control R. So that will reset it too, but Control R will definitely reset your RAM. So you have to remember to make sure the clock is low to start off with. That's one thing that we cannot get around with. So we'll load the RAM image using subtract. Okay. And we are ready to go. Of course, the first question is, do we just check register A when we're at the halt instruction and just assume that's all good? How do we make sure this program works? How do we use this program and understand how stack is actually utilized by the caller, the callee? We want to trace, right? We want to trace a whole bunch of stuff. Okay, so if you're studying for this class, this is how. If I'm studying for this class, this is how I'm going to do it. So I would look at, the various. The program counter is the first thing that you should track all the time, because the program counter tells you where you are at in the program. It is usually one more than the location of the instruction that you're executing, but knowing that, it does tell you where you are in the program. Okay, so the program counter would be one thing that you always want to track. In this particular case, inside the register bank, we got a few things that we also might want to track. Register D for sure we want to track because that's our stack pointer. We are trying to understand how the stack is utilized from the caller's perspective and also from the callee's perspective. So the stack pointer is going to be important. But we also know that we also use register A and B for various purposes. So those two are also useful. Now if we're tracking all of those things, we might as well make those in order. And let's see, I guess we can move up. This is register D, so we can move it down twice. And do we want to track C? Register C is not utilized. Okay, so we don't have to track that one. All right, so we got all the registers, but we also have RAM locations that we might want to track. The beginning part of RAM, we're not interested because we only want to keep track of what the stack might be using. And in this case, location 255 is definitely used. This is where Y is stored. This is where X is stored. This is where the return address is stored. So those three locations we want to track. We might as well track here 2522 because that one should not be touched at all. Is that okay?
the same idea. You should log register C, right? Make sure it's not being used.
Say again?
I said the same idea works for looking at the other register.
Right.
Make sure that's not being used as well.
Well, if you want to double check that they are not used, you can track those too. Right? Correct. Okay, so you can also track it in a file. So the moment you specify a file to do the logging, so I can just use subtract.log as the name of the file to track all of this stuff here. Save. Now all the output will be in the file. Okay, so I've specified everything I want to track. So it's now time to start the simulation. So I can just say enable and just let it done. It's all done because the program counter is no longer changing, and also the instruction register has a value of 01, which means I'm executing the halt instruction. So Control K one more time will stop the clocking, and now I can go take a look at that file. So we'll go to that folder, go to the temp folder, and take a look at subtract.log, which is the log file. And it's a little bit hard to read because it is very wide. It's wider than I have space width-wise. So let me rearrange the terminal so that we get enough space. No, I have to change the font size. There we go. Okay. So this is really useful because this is something that you can do after the execution of your program. Okay. So we can look at the stack, how it is used.
Like the matrix right there.
Sorry? The matrix?
I'll make a joke. It feels like I'm reading the matrix right here.
In a way you are, because
Yeah.
the processor is being simulated, right?
It's not strings of
From the
data, but yeah.
from the processor's perspective, it is still inside the simulated world. Okay, so we can see how the stack is being used. We can see this is location. Let's see here. The program counter is the first one, which is this one. Then register A, register B, register D. This is location 255, 254, 253, and then 254. Okay? So you will see that this column will get changed because it's the return address. Okay. So are there any questions about the trace at this point? So what we are particularly interested is what is put onto the RAM locations. Okay, the RAM location here, what is this? And what is this? This is parameter Y. This is parameter X, right? And after the calculation, what should end up in register A? 5 minus 3 is 2. So when we scroll down, when you look at register A did end up with a value of 2, which is correct. And where should the program end up at? It says right here, it ends up at location 13, which means the halt location is at location 12. You can double check with your assemble tab in the assembler, and then you just highlight the row containing the halt instruction, and it is in fact at location 12 in hexadecimal, which is the decimal 118. So we double check everything, and the stack was used the way it is supposed to. And then the other thing you can also check with just this text file is to look at how the stack pointer changes. The stack pointer was initialized to 0, and then it got decremented to 255, and then location 255 got something. And then it got decremented to 254, and then shortly after location 254 got something. And then it got decremented again to 253, and then we can see location 253 gets a value right after that within the instruction.
Why is it doing 6 spots for the
Why is it what?
like on the I guess the D pointer or 25? You see like there's like 6 numbers every time it goes to decrement or go up, I guess.
Like
Yeah, that one. Yeah, like there.
these
like,
6?
Yes. Why is it 6?
Okay, so the program counter indicates that we are executing location. This is 8. Okay, well it's 9, but it is actually corresponding to location 8.
Right.
So location 8 to location 12. Okay, so basically A to C are basically what we're looking at. So there are multiple instructions to get the stack ready. Some of these are changing the register A. You can see
Right,
how
those are
register A is
instructions.
changed right here. Some of those instructions are changing this part here. Well, actually not 6 of them, because there are only a few instructions. But basically when you look at the program counter, subtract this by 1, it will tell you which instruction is responsible for the rest, what changes of the rest of that particular line.
And the deeper you go, the more instructions there are. The deeper in level you go, the more instructions there are. Because I see that up top it's 5, and then below that it's like a bunch for the counter. For the counter,
It's the instruction number, right?
You mean this part here?
No, the fourth
Column?
column. Yeah.
You mean here?
Or, yeah, that one. Yeah. That's what I'm looking at here. 'Cause that's the address of the.
This is the stack pointer.
Yes.
This is register D. So register D maintained at this location because we are doing something else that is not changing the stack pointer. So we have to initialize the other register to get a value, right?
Yeah.
And then we have to then we decrement. So we are looking at right here. This change is the decrement of D. After we decrement D, what do? We do a store, right? And then we get another register ready, and then so these are the operations you're following that.
We store that, we decrement that register's address until we get to.
Right, so when you look at location, so let's go to location 8 of the assembler and find out exactly what is going on. So we're looking up location 8, which is this one. Okay, so this is the decrement D instruction. So right after this, we store A to whatever D is pointing to. So that's not changing D, right? It's just saying, okay, D, wherever you point to, we're going to store a value right there. And then we have the LDI instruction, which also does not change D. And then we have the decrement D instruction, which changes D. So we should be looking at another change at location C over here.
Makes sense. Thank you.
But some of those instructions take up 2 bytes, and that's why you see the program counter.
Yeah, because there's four lines, but then there's probably 5 or 6 instructions.
This one takes up 2 bytes. The LDI instruction takes 2 bytes.
Right.
Because the first byte specifies LDI and which register we are changing. The second byte specifies the value that we're using to update it.
Instruction 8 or instruction 8 also takes up 2 bytes as well. Because
Which one?
Instruction 8 store, because we're
The store, yeah, that takes up only 1
only
byte.
one. Okay.
That takes up only 1 byte because where it is storing is
These are
already
already
specified by the
allocated.
register.
Got it.
It's specified by the register. We're not saying exactly where, but we are saying, okay, wherever register D is pointing to, that's where you want to store it.
Which already has a byte allocated for it, right?
No, we don't need to allocate because it's on the stack.
That's right.
Yeah, this is on the stack. So you can sort of say that we allocated that byte when we decremented the stack pointer.
Yeah, what about the LDI?
The LDI instruction has 2 bytes.
Has 2 bytes.
So the LDI instruction, which is on row 6 here, it is at location 6, right? So we can go back to the trace and we can see that location 6, which is registered, or it will show as 7. So these 2 instructions, or these 2, okay, 6 and 7, there we go. It stayed at location 6 twice because something else changed. You can see how this byte is changed. This is the store instruction. Is that right? Yep. So this is the store instruction, storing the 3 at location 6. Okay, when we go back to here, location 6. This is 5. Oh, by the time we get there, it is execute. By the time we execute the store instruction, the program counter is already at location 6. Because it generates 1 row whenever at least 1 thing is changed, whatever you have specified to watch. Yep.
Also, does the program counter change when you're increasing or decreasing the D value in the register? The address when you're shifting it?
When you execute any instruction, the program counter changes. Yeah. So is that okay? I mean, this really shows you how the program executed the code. Because we are tracking how the stack is used, how the stack pointer is used, and how the various registers are being used. So are there any questions about this process? Because from here on, this is basically your only way of debugging your program.
Why you like binaries so much?
It's definitely useful. Assembly language programming, some people can compare that to building castles, but out of single, individual grains of sand. It sounds really tedious and impossible, but it is actually okay because you make small structures out of individual grains of sand, but then you can make bigger structures out of those small structures, and they can get bigger structures out of those smaller structures. So yes, compared to C programming, it is more tedious. But beyond a certain point, when you have all the subroutines and whatnot done, things actually get easier.
It's kind of free.
Sorry?
Just copy paste and everything. Once you have the subroutines done, you just copy paste them into place, and as long as
You just call the subroutine. Yep, you just call the subroutine. Copy and pasting is not something that we want to do. If we can avoid it, we don't copy and paste. How many people have taken CISP 400? Object-oriented programming class. So when I taught that class, I taught that class by exposing what C code is responsible for a C++ construct. And I'm doing the same thing with this class. I'm showing you what assembly code is responsible for what type of C construct.
Printf and cout gone.
Right, but also, how do you use methods and how do you access properties or attributes of each object? Yep, go ahead.
Have you ever asked us to change assembly language code into C code? But like, for example, I know C++, but I'm not familiar with C, every little avenue. Do we have to know C essentially like the back of our hand, or can we like do C++ code and it's kind of close enough?
Well, C is a subset of C++,
Right.
for the most part, not entirely.
For the most part, right, but I might like miss like a corner case here or there. I might not know in C that.
I don't see how that would come into play in this class, because I will ask you guys to reverse code.
Yeah.
Like, I will give you the assembly code, and then you have to give me the C equivalent code.
Yes.
But it's not going to be in a case where you can use C++ really.
Because we're not like C-adding or anything, because we're like doing anything that requires.
Give me an example where you.
I can't think of one off the top of my head. But that's why I'm asking.
Okay, I don't
What
think.
comes up?
I don't think there will be a scenario where you can use both C or C++ notation, because there's no object orientation whatsoever in this class.
Okay. The only thing is like, for example, in C++, unsigned int is for that, and then uint or underscore 8 or 64 is for C.
That's not a C versus C++ feature.
That's just a library.
That's a matter of pound including the header file.
Okay.
So that has nothing to do with the language itself. It's just what header file are you pound including. If you're including stdint.h, which is standard integer.h, you can use all those things in C or C++. Yep.
Okay.
It is just hard because, I also know C++, but I'm not as familiar with C, so I couldn't tell you what we might.
Yeah. Like, I feel like there might not be a problem, but I'm afraid that if it comes up, I won't know what to do in that case, especially if it's like an exam. You ask us to reverse engineer.
Okay, so instead of saying C code, I'll just say whatever language you learned in CISP 360.
Sure. What if it's Java?
Because that's the bottom line. That's why that class is the prerequisite of this class.
Okay.
So I would just say whatever language you learn in CISP 360, use that to express this assembly code. Yep.
So we haven't technically learned in the past. We haven't really created variables. We just put something onto a stack.
Not variables yet.
Yeah.
Okay, but we dealt with parameters. Variables are pretty much the same way. Okay, so I'll use this picture as the end of this lecture, because it will serve as a reminder of where I should begin next time. Okay, so when you look at how the stack is used, okay, from the perspective of calling a subroutine, you have parameters. Okay, so this is param 2, param 1, and then you have the return address, which is where you have to go back to when the subroutine is done. This space here can be used for local variables. So local var 1, local var 2, and so on. In other words, this is the caller's responsibility, and this one too. This one is kind of shared. So the caller responsibility are these three, and then the callee's responsibility are these three. So the callee is responsible to allocate and maintain the area for the local variables, But the callee is also responsible to deallocate the return address. So that's why the return address is kind of shared responsibility. The caller puts it here, the callee has to clean it up.
Yeah.
So the local variables are pretty much the same thing, except it's on the opposite side of the return address. But they are on the stack too.
Pass by value doesn't exist.
It's always passed by value. If you want to pass by reference, then whatever the parameter is the address of something else. So we'll talk about all of those things later. Yeah, but today we are just focusing on the return value and also the parameters. All right. So I'm hoping that you guys are at least getting started with the homework assignment due on Wednesday. And once again, when you use LogicSim, okay, just keep in mind, I just want to point this out one more time. Just keep in mind that the reset button does not deal with the clock. So if your clock ends up to be high, light green, and you want to start the program all over again, just make sure that you turn it low manually. I cannot think of a way to do it manually, automatically. So that's something that you just have to kind of pay attention to, unfortunately. Because Control R will work, but Control R will also clean the RAM content, which means you have to reload your program into RAM again. So if you want to save yourself that trouble, then you have to make sure that your clock starts low when you start your program.
Connecting the reset button or the wire to clock wouldn't change it.
There's no way to connect it.
No,
Yeah, because clock is like an output pin, an input pin. It only has one single place of connecting, and yeah. So when you look at the clock pin, it says duration. You can change the phasing, but you cannot change. You cannot say, okay, when the reset button is clicked, reset this one to a low state. You cannot. There's no way to specify that.
Weird.
Yep.
Could you make a advanced clock circuit out of a clock so you can implement a reset button?
Like an exclusive
Make your
something.
I'm not saying it'd be an easy thing or even a good idea, but
Don't give them any ideas.
I'll think about it. There might be a way to do it. I'll think about it. I'll see you guys in the lab.
All you gotta do is make a clock.
To make it split so that it